Google's infrastructure has been the source of inspiration for research papers, software projects, and entire companies. Google pioneered the idea that we care less about the individual machines that we are running our applications on, and more about the applications themselves. Containers are the abstraction that we use to separate the concerns of the application from those of the underlying hardware. CoreOS is an operating system built with this paradigm shift in mind. In a data center, the main job of the operating system is to be a platform for containers to run smoothly on. Brandon Phillips is the CTO of CoreOS, and he joins the show to explain what CoreOS does differently to power the applications that get deployed on top of it. Before we get to this episode, a few quick announcements. If you're interested in advertising on Software Engineering Daily, send me an email, jeff@softwareengineeringdaily.com. There are more than 14,000 engineers that listen to Software Engineering Daily on a regular basis, so it's a great place to get your product out into the ears of developers or to advertise available jobs that you might have at your company. Also, if you're an engineer that's looking for an open source project to work on, check out Software Daily at softwaredaily.com. This is an open source news and information site about software. It's being led by Jeff Tribble, a member of the Software Engineering Daily community. You can also check out softwareengineeringdaily.com, which is the website for this podcast. You can find links to the Slack channel, my Twitter account, my email. You can find a link to sign up for our newsletter, Software Weekly. And with that, let's get to today's episode. Getting started with Kubernetes can be a challenge. If you don't know where to start, go to aprenda.com/sedaily. There's an upcoming webinar about installing Kubernetes, as well as an introduction to Minikube, which allows you to run Kubernetes locally. At aprenda.com/sedaily, you can also find past webinars about Kubernetes, covering microservices, persistence, and multiple clusters, as well as the history and origins of Kubernetes. And if you're looking to move to a cloud-native infrastructure platform that works with your existing applications, you should also check out aprenda.com/sedaily. Aprenda provides cloud platform software that works with your existing applications and infrastructure. So whether you're looking for a guide to installing Kubernetes, or you're looking for a platform that will give you access to cloud-native infrastructure that works with your existing applications, check out aprenda.com/sedaily. That's APPRENDA.com/sedaily. Thanks, Aprenda, for being a sponsor of Software Engineering Daily. Now let's get back to this episode. Brandon Phillips is the CTO at CoreOS. Brandon, welcome to Software Engineering Daily.
Thanks for having me.
There is a paper that I have heard you reference that was published out of Google called The Data Center as a Computer. The idea of this paper is that we have moved to a world where we no longer treat infrastructure with a concern for the individual machines we are deploying to. We want to think more in terms of our applications. When did you read this paper, and how did it change your thinking around building systems?
Yeah, so sort of read this paper as I was winding down my experience at Rackspace, and it was really coming through pretty loud and clear that in the day and age that we started CoreOS and that we were thinking about these problems, that data centers were becoming more about supporting applications and less about actually building out the infrastructure themselves. And so, it was coming around the time that we were forming some of the initial work on CoreOS, and as we were coming off our experience having ran applications and helped to run data centers at Rackspace.
So, how did those problems manifest in your work at Rackspace?
Yeah, so at Rackspace, I was working on a product called Rackspace Cloud Monitoring. And on that product, we had like a globally distributed application. And a lot of our time was spent not necessarily focusing on that globally distributed monitoring application, but more time was spent, figuring out which servers to buy, what hardware configurations were necessary for the software that we were using, and then inevitably building out that whole pipeline of software from configuration management, and build systems that would actually end up landing copies of the code onto the hardware. And so this is like a very common pattern for a lot of people is they have an actual application that they want to build, but they spend a lot of time thinking through these things that really are pretty common to every product, any software product that you build that has a hosted component of this lifecycle management of the application, setting up monitoring, capacity planning of the hardware, thinking about which pieces of hardware are going to run what application and this sort of thing. And to a large degree, those things in this day and age, and more so over the last few years, are things that can be automated, and that computers are pretty good at balancing and calculating and placing applications these days.
And as we move towards this world where we're thinking about the data center as a computer, how do containers fit into this way of thinking about building systems?
For sure. So the whole theory with this data center as a computer idea is that we're thinking about not the individual like hard disks. We're not thinking about the individual blades or the individual machines. We're thinking about essentially taking some capacity, some memory and some CPU and some network capacity, and running the thing that we want across a fleet of machines. And we really don't care about the individual server. The individual server is something that's easily replaceable. Oftentimes will fail without human intervention and this sort of thing. So the reason containers are important in this world is because you really seamlessly need to be able to move an application between one machine to the other. Going back to this idea that in a data center as a computer, any machine may fail at any time, you need to really make sure that this application is this atomic, consistent little thing that can be moved from host A to host B and ran in the exact same way as it was on the original machine. So that's really where the container starts to play its role. It's this consistent atomic piece of packaging around a piece of software application that you actually care about in the data center.
What did Docker do that was new about containers? How did the Docker engine get so popular?
Sure. So when we started CoreOS about 3 years ago, Docker hadn't been started yet, and largely containers continued to be ignored as a way of isolating and packaging up software. You saw a lot of successful companies building on top of containers. A very notable example of this is Heroku, a software as a service platform for building and hosting web applications. But the user wasn't really aware that Heroku was using containers behind the scenes. And in order for the things that we wanted to build to work, we needed containers to be brought to the forefront as something that developers and operations people thought about as a way of packaging and distributing applications. And that distributing applications part is really the part that Docker got correct and brought to the market, was this idea that containers aren't this complex machinery that you need to kind of custom do on every single host. It's actually something that you can package up, push up to the internet, similar to how you do like a git push for your code, and pull down onto other hosts. And so this idea of being able to package up really trivially and distribute software is really what made Docker successful and what brought containers to the forefront of the discussion that we have today around all these distributed systems and Kubernetes and this sort of stuff.
So there were these variety of other container runtimes, Google LMC TFY and Cloud Foundry Garden, and Mesos had a container specification. Why were there so many container specifications? Was there something that Docker did that was dramatically different than these container specifications, or was it more this like virality component, the usability component?
I think it's still like things like Garden and Let Me Contain That For You and LXC and a lot of these projects that came and that we associate with containers, none of them really tackled the problem of how do I get the container that I want to run onto my host so I can run it. And that was fundamentally the difference that that Docker approached and tackled that problem of how do I get the software that I want to run there. And so, the primary thing is they didn't punt on that problem, and they figured out a way of packaging it up. Now, to a large degree, all the other container runtimes have started to adopt that idea. So this idea of having a container image that's hosted on the internet that you can download, you're starting to see things like Cloud Foundry adopt those. Clearly, things like Kubernetes are built on this concept and rely on that sort of concept. Bezos has started to implement container runtimes into their platform. And that's why things, we can talk about it later, but things like making sure that we standardize how these containers work, and so that we can interoperate and that the developer can move their container around different platforms starts to become really important. But yeah, it's all about this container image and this idea of moving it around.
Right. And so the degree of standardization, the ability to move our container around to different platforms, what is the state of that today? How portable are the containers that we are building?
Yeah. So it's improving. The portability all just comes down to having some agreed upon semantics, like anything, like HTTP and HTML5 that happen on the web. It all just comes down to essentially having some agreed upon semantics for how these things work. And I think the semantics are pretty solid at this point. Everyone has a pretty good idea of how this stuff works. And the technologies involved to create a container image are actually pretty straightforward and easy to implement. And so at this point, what it comes down to is syntax and ensuring that everyone agrees on the exact implementation. And that's where things like the Open Container Initiative are making progress. And that work is ongoing and involves a lot of the really important folks in the industry. Docker and CoreOS and Microsoft and Google and Red Hat, et cetera, are all kind of involved in that effort.
Yeah, so I didn't prepare much around the Open Container Initiative for this interview, but I am very curious about that. I know there are some listeners who are curious. Could you just talk about what are the main points of debate or discussion or technical development that the Open Container Initiative is intent on solving?
Yeah, so the main thing that we're focused on solving is making sure that somebody who wishes to run a container on a machine understands how that process will actually be set up, what sort of environment can it expect to land in, that sort of stuff. And also a software engineer who is just wanting to package up their software inside of a container. How do they package that up into a container image? What sort of metadata goes along with that image, like the license and the URL for the homepage, and how is that artifact actually assembled using like tar format? How is it compressed? How do they sign it? How does a cryptographic hash, like a unique identity of that thing, get generated? That sort of thing. So those are the two sides of the Open Container Initiative and what it's focused on, ensuring that there's well-formed standards around.
Okay, so getting back to talking about this space a little more broadly,
sure.
Just so we can move towards a conversation around CoreOS. So, the workflow for a developer who is writing code that's eventually going to wind up on a container is the developer is working on code, the developer pushes a commit to a repository, and that code winds up in a container deployed on infrastructure somewhere. And ideally, the developer doesn't have to think much more beyond that. But there are obviously a bunch of steps that happen in between those two states of pushing a commit to a repository and that code going to deployment in a container on infrastructure somewhere. What are the important steps that are going on in between those two things?
Yeah, so today there's a lot of different ways that we found customers are actually building that final artifact, building that final image. We have people who are doing a lot of ad hoc stuff, so they'll just have the developers build the image using their laptop and then push to a central registry like our product Quay.io. We have folks that will, like you said, essentially abstract completely away from the developers the concept of a container being built. So the developers will push to a Git repository. That Git repository will then get triggered by something like Jenkins or some other CI/CD system. That CD system will actually build the container and then push it eventually into a registry like Quay. And so there's various shades of gray in that spectrum, but essentially anywhere from people doing kind of the ad hoc, it worked on my laptop, I built a container, it should work in prod, to we have a very rigorous existing CI/CD environment that our organization is used to using, and we adopted that existing testing and build environment to output a container image. That's a little bit more common in more mature organizations where perhaps they had some other deployment style in the past and they're moving to containers for the application moving forward. And then obviously people who are getting started are much more apt to use it worked on my laptop, I'll package it up and push it to the repository and see what the rest of my engineers or the rest of my team want to do with that.
So how do the responsibilities of the operating system that our containers are running on, how does that change when the only thing we're doing with that operating system is simply running containers on top of it?
Yeah, this is a great question, and this gets to why we built things like CoreOS Linux, which was our first product. The operating system starts to shrink dramatically. Before containers, we relied on our operating systems to do a really complex set of things for us. We relied on them to keep our databases and our language runtimes and the Linux kernel and our bootloader and all these disparate pieces of software that have each their own life cycle. And we asked them to keep those pieces of software up to date and to never break the APIs between the pieces of software. So all those pieces should work together. And then at the same time, we'd be making demands like, well, I want also the latest version of software. I want to be running the latest Python or the latest Java or the latest Postgres database. And so it's a really hard set of demands. And so with CoreOS Linux, we ship just a handful of pieces of software on the operating system, essentially things that are necessary to bring up networking and storage and then run a container. And so on CoreOS, you're not going to see things like Python or Ruby or these sorts of things that an application might use because they're unnecessary, because those things run inside of the container. So it can be a little confusing for people using a CoreOS Linux machine for the first time, seeing that their expected tools aren't there. But to a large degree, CoreOS Linux is not designed for human beings to interact with. It's designed for running containers, and that's about it.
So we have had some shows recently about unikernels, and a theme that both of the unikernel guests that we had on said is that the Linux kernel in its current state in most distributions has been trading off efficiency in order to be compatible with all of the different types of applications that could potentially be deployed on top of it. So what is an example of that excess of compatibility that the Linux kernel accumulates rather than optimizing for efficiency?
Yeah, to a large degree, I continue to be extremely confused by unikernels. The idea of a unikernel still fundamentally relies on hardware abstractions, and the hardware abstractions are coming from the Linux kernel. And so really, like, the inefficiencies of the Linux kernel don't come from needing compatibility with applications. It comes from having to deal with and abstract away hardware to a large degree, and that's what causes and that abstraction is extremely useful, right? Like, we can log on to a Linux machine, whether it's manufactured by HP or Dell, or even if it's running separate architectures, whether it's an ARM machine or an Intel machine or whatever it is. and they behave roughly the same, and those APIs are roughly the same. And so the abstraction is still useful. Now, the unikernels rely on that Linux kernel abstraction to then implement applications that are utilizing really, really efficient APIs. But to a large extent, like the abstraction that Linux is providing is fairly efficient and extremely useful, even if you're building a unikernel. Now that said, the Linux kernel could be doing a better job at like how the network APIs are built, how the file system APIs are built, and we are relying on an API layer that is, now at this point 40, 50 years old. The POSIX interfaces are showing their age at times, but it's a pretty effective hardware abstraction, and it continues to be.
Now, CoreOS is this minimalist operating system, and I feel like we should define what CoreOS is. I'd love to hear your take on how that contrasts with what the goals of unikernels are, but we should probably start at the basics. What is CoreOS?
For sure. So CoreOS is two things. First is it is a 3-year-old company that's building a bunch of technologies around containers and distributed systems. And then CoreOS Linux is a product that we built that is a Linux operating system that's super minimal. So we'll talk about kind of the story of how we got started with CoreOS Linux. When we started to go down this path of wanting to, what we ended up calling Google's infrastructure for everybody else, but when we went down this path of wanting to build products to help people run their infrastructure in really efficient ways, we wanted to essentially from the very bottom of the stack create a set of software open source projects that did it in what we would like to consider the correct way. And so with CoreOS Linux, what we wanted to do is we wanted to strip out everything that wasn't necessary in order to run a container, reduce sort of the surface area for vulnerabilities, the surface area for introduction of complexity and backwards compatibility issues to the very minimum inside of an operating system. And then that would free us up to do some interesting things. One of which is that we knew that the container ecosystem would be moving really, really fast. And we wanted to have an operating system that could keep up with that pace. And then also we wanted to solve this problem of security updates. All software has security vulnerabilities. It's just a matter of time before they're discovered. Even the most secure thing in the world, lockdown, burnt into hardware, inevitably gets some sort of issue in it. And so in that way, CoreOS Linux differs from a lot of other operating systems built for servers in that we have a atomic auto by default upgrade system. And so the CoreOS, machine running CoreOS Linux by default will just automatically be upgraded to the latest version of the operating system over time.
Yeah, I was going to say, talk in more detail about how those updates work, because CoreOS has no package manager. So the way that it does updates is quite different than typical Linux systems.
Yeah, so the way CoreOS Linux does its updates is very similar to how our phones do our updates or how sophisticated networking equipment do their updates. So CoreOS has a A copy and a B copy of the software on installed, and then it will download a new copy of the software and place it on one of the A or B partitions of the disk. And then when it's gotten the signal one way or the other that it's okay to reboot and apply the update, it will atomically move from one version of the software to the other. And this has a number of nice properties. One is that it's really trivial to cryptographically verify that you're running a correct version of the operating system. Two is that you know for certain that you're running either the A or B version of the OS. It's a really common problem inside of traditional Linux package managers to be partially through an upgrade or partially reconfigured onto the latest system, or partially running the latest version of the kernel because some of the modules you're actually using from the new version of the kernel, et cetera. So there's a number of different corner cases that we avoid by having this very atomic, very consistent thing. And this atomacy and the consistency is really important once you think about managing more than a handful of machines. One of my favorite stories of outages when we were maintaining the cloud monitoring product is that we had this nice distributed system, 5 data centers, and we had a cron job that would do automatic apt update and upgrades when somebody was on duty. And so to a large degree, we'd automated the updates, but we hadn't been paying attention to whether we actually rebooted the machine onto the latest kernel. And so there's this terrible Linux kernel bug where the machines would just lock up when the leap second happened. And so we lost 2 of our 5 data centers simply because not even that we weren't applying the updates, it's that we hadn't fully applied the updates. So it looked consistent because the new kernel packages were there. It was actually inconsistent because the kernel installed was different than the kernel that was currently booted. And so these are very common operational problems, and we really wanted to hopefully automate, or at least help pave the way for administrators to automate their way out of a lot of that, those sort of accidental situations.
Now, when we're talking about this atomic ability to update the software and switch it over, is this only applicable in a situation where there's like an update to something within Linux, or is this also how we want to do continuous deployment on our infrastructure that is running CoreOS?
Yeah, so when we were thinking about fixing problems all the way down to the bottom of the stack, and why we started by building CoreOS, is that absolutely this is how application deploy should be done too. You want to bring up the new version of the application right next to the old version of the application, which is something that's really difficult to do today. Say that your new version of the application requires Java 7, but the server currently has Java 6 packages installed. It can be a huge rigmarole for organizations to be able to do these sorts of updates. But you want your applications to be always in a safe spot. You don't want to incur downtime. You don't want to give your users a bad experience. And this is where containers start to solve some really fundamental problems with how we've operated and thought about operations on Linux servers. And so by using things like Kubernetes, by using things like containers, you start to have the APIs and start to have the technology in place that you can say, we're going to run version 1 of the application, and then we're going to spin up some copies of version 2 of the application, and then we'll slowly move load balancer capacity over to version 2. And you know what? If we find out there's a bug in there, we can immediately roll back to version 1 because we have hot running copies of version 1 that aren't taking any traffic, but they're available on our hosts. And so it is very much a pattern that gets repeated up the stack, and fixing it at the bottom of the stack was something that motivated us to create CoreOS Linux to begin with.
Continuous integration is so useful that I've started using it on my own personal projects. SnapCI from Thoughtworks has the fastest setup I've ever seen. I registered for SnapCI with my GitHub account, and after a few clicks, I had continuous integration pipelines set up for a Node.js application and a Rails application that were just sitting on my GitHub account. And I don't want my users to experience breaking changes, so I want to run a large suite of tests for my application every time I push a change. And SnapCI will run those tests quickly, in parallel, on a worker that SnapCI spins up and takes care of for me. Whether you have personal projects like me, or you work at a company that is looking for the perfect tool to improve the deployment process, go to snap.ci/softwareengineeringdaily. SnapCI embodies the lessons that Thoughtworks has learned from 20 years of software deployment, the same lessons that have been written about by Martin Fowler and Jez Humble. Check it out at snap.ci/softwareengineeringdaily. It would support Software Engineering Daily, and you would get to check out continuous deployment. snap.ci/softwareengineeringdaily. Thanks for listening.
So
So not to jump ahead, but the typical model for when you're deploying a container on Kubernetes is you've got these pods and you allocate allocate some amount of space to the pod, and then you spin up a container that takes up some amount of space within that pod. So within the CoreOS model, if you're going to have two simultaneous versions of the application running at a given time, and then you're going to switch the traffic between the two versions, does this mean that the allocation strategy for the pods in Kubernetes, if you're using CoreOS, does that differ significantly than if you're not using CoreOS?
No. So for Kubernetes, CoreOS is just like any other operating system. So you say give your application a gig of RAM and 20% of the CPU, and then when you spin up the next copy of your application, the new version, you give it similarly a gig of RAM and 20% of your CPU. And it doesn't matter much to Kubernetes how the operating system is doing that. So to a large degree, CoreOS Linux is just kind of a boring any other compute node to Kubernetes.
Sure. Okay, so before we get into the scheduling stuff, let's talk some about etcd. CoreOS is designed for the host to be able to fail. So you're running on this commodity hardware that happens all the time. You have failures. What are the different steps that CoreOS takes to equip an infrastructure that is running CoreOS for that type of failure?
For sure. So for some context, CoreOS builds like a number of different open source projects, and the first two that we built are CoreOS Linux and etcd. Those continue to be pretty important and flagship projects for us, and they both get a ton of adoption in various products and projects throughout the web. And so the motivation for building etcd, which is our consensus data store, inspired, if you're familiar with some of the Google literature, inspired by a Google service called Chubby. What etcd is trying to do is hold on, no matter through any number of machine failures, hold on to really, really important cluster configuration data. And so this really important cluster configuration data are things like, what are service discovery information? Where can I find other services in the cluster? Secret storage, what is the username and password to the database that this application is supposed to be connecting to? Network configuration, where are the routes, who are the gateways, etc., to get access to the rest of the cluster. You can imagine starting to build other sorts of systems on top of etcd, like storage. I need to know where the disk is, where the log volume is for this particular application, etc. And so what etcd does is it exposes a key value store. So you can set some keys, append some values to it, and then it replicates those keys and values around multiple machines. So if you have, in general, by default, we recommend a 5-machine cluster. When you write into etcd, it replicates the data between the 5 machines and the etcd cluster and does a lot of different things to ensure that that data stays resilient and safe over time.
So I have 5 machines that are storing the configuration data for etcd. How big of a cluster can that level of replication support?
Yeah, so a 5-member etcd cluster is something that can quite easily, let's say that so etcd is a database, and one of the applications that uses etcd as its database is Kubernetes. And Kubernetes, you can scale up to 1,000 to 3,000 hosts today using etcd on a 5-member cluster. And so easily in the near future here, as we continue our scaling work inside of Kubernetes, you'll be able to see etcd scaling up and supporting 10,000 machines inside of a Kubernetes cluster. So this very small number of machines sort of act as the managers, and the managers need to hold on to this important data. Even if one of the managers happens to fail, have a hardware failure or reboot or whatever. And that's the job of etcd, is to ensure this really important data that's required for these 1,000, 10,000 machines to continue doing useful work remains resilient and doesn't get lost.
And I guess, what kinds of information am I storing in etcd, and how does that information get propagated to the whole 1,000, 2,000, 10,000 node cluster from these 5 nodes that are storing it in a replicated fashion?
Yeah, so the data that is generally stored in etcd is data that was put in by the operators of a cluster. And so, like I said, it's everything that you would imagine is necessary for your application to run. So it's network configuration data, service discovery information, storage information, secret stores, etc. So anything that a human being has to put in so that the machines know what to work on, that's what you store in etcd. I guess the other piece is like scheduling information in the case of Kubernetes as well, is being stored inside of etcd. And then etcd has a number of primitives that make it easy for system administrators to audit what's going in there and back up what's going or what's being stored in the data store and that sort of stuff.
And so how does that information get propagated to the rest of the cluster?
Yeah, so the data gets propagated through APIs. etcd is like any other database, so the other members of the cluster connect to etcd through a network socket, talk over HTTP or HTTP2, and pull whatever data is relevant for those other machines out of the cluster.
So are the other machines in the cluster periodically pinging etcd for changes?
Yeah, it really depends on the application that's built on top of etcd. So in the case of Kubernetes, what happens is that every single node in the cluster has a particular endpoint that has all the information that node needs to operate. And so each node will talk to the Kubernetes API server, which is then backed by etcd, and on a regular interval say, do you have any work for me? And if there's any new work, the API server hands it back based on what's being stored in etcd. And so it's pretty classic, like leader-follower sort of centralized architecture.
Sure. So there are some similar systems to etcd, like Zookeeper, Console. What are the design differences between those types of systems and etcd?
Yeah, so when we started building etcd 3 years ago, Zookeeper was the only incumbent system. And the main things that we wanted to do differently with etcd than Zookeeper, I had a bunch of operational experience with Zookeeper previously, were that we wanted to build something that was, what's now being termed as cloud native, but that was appropriate for the cloud. And one of the things that meant was that you could dynamically reconfigure the cluster. So this means like through the command line, while the cluster is still live, I can add and remove machines from the etcd cluster. This is something that until very recently, and I don't even know if it's made it into release, Zookeeper was unable to do. And it's really important if you want to run these sorts of systems on Amazon or Google Compute or somewhere else where machines come and go at least on a weekly basis, if not more rapidly. And so that's the first design thing. It's just making sure that this was a piece of software that was sort of cloud enabled. The next bit is we wanted to lower the barrier to entry to distributed systems. Zookeeper was always perceived as this really complex, hard to use beast. And really the concepts that etcd exposes are very straightforward, fairly easy to understand. If you've used SVN or CVS or something that has this linear revision history, you have a pretty good idea of what etcd is doing. And so etcd exposed, instead of a kind of proprietary binary API, it exposed via HTTP, where you could curl and play around with the API just using any HTTP client off the shelf that your language or your command line gave you. And so we greatly reduced the barrier to entry to using these systems, and then we saw a huge proliferation of projects starting to build on etcd, which really any distributed system needs this consensus piece, this core piece that etcd provides. And so by lowering that barrier to entry, we found that a huge number of new applications were built. It was pretty impressive, and it's been shown to be a pretty good building block. And that's how things like Kubernetes ended up getting built on top of etcd.
Right. So it sounds like it's not like you did anything revolutionary in terms of the consensus protocol. It's Raft based, whereas Zookeeper I think is Paxos based. But ultimately, the breakthrough you made was more in the usability, the API.
Yeah, there's actually Raft was pretty important as well. By choosing Raft, we got that dynamic reconfiguration ability. One of the things that the Zookeeper Zab, Zookeeper is not actually based on Paxos. It's based on this Paxos-ish protocol called Zab. And Zab, until very, very recently, didn't have the ability to do dynamic reconfiguration, which is a prerequisite for this sort of cloud enablement that we were going after. So choosing Raft and the design of Raft was actually fundamental as well.
Okay. Well, let's talk about scheduling. We had a show recently with Adrian Cockcroft where we talked about scheduling, and that word can obviously mean different things in different contexts. In the context of CoreOS, what is being scheduled and how does that scheduling take place?
Yeah, so for CoreOS, we have a couple of different scheduler projects that are kind of associated with us. We built a container scheduling system called Fleet really early on. And Fleet was a very, very simple scheduler that exposed something that looked like a regular init system like systemd to the user, but that init system was spread over a lot of hosts. And then the other scheduling system, which we are really deeply involved with, is Kubernetes. And Kubernetes is probably the more relevant one, as Kubernetes has gotten a lot more noise and traction in the overall ecosystem. So let me talk through that. In the case of Kubernetes, what we mean by scheduling is we mean the ability for a system administrator or a set of operations people to run, let's say, 20 machines, and to make those 20 machines available for anyone to run their application, their containerized application on top of. And what the scheduler is in charge of doing is the scheduler is in charge of identifying which machines have resources available to run jobs that are submitted by the human beings, and finding what are the best fits for those things. So ensuring that various constraints are maintained. So constraints might be things like, I want to ensure that task A and task B are never on the same physical host. Or I want to ensure that this task C lands on a host that has a GPU, etc. And so that's really, in scheduling, it's about ensuring that applications land on some sort of host and begin to run based on user input of constraints and resource requirements.
Now, in a distributed system, one thing that needs to be scheduled is the update and reboot process. We talked about this a little bit earlier. CoreOS provides a tool called Locksmith for this scheduling. What is Locksmith?
Sure. So let's say I'm the operator. I have these 20 machines. And on those 20 machines are running a very critical application that I want to ensure stays up because I don't want to get paged. But I have this competing thing that I also want to ensure that security updates to the underlying operating system continue to be delivered. And so I have these two goals that are kind of at odds, right? Like I want to ensure that as rapidly as possible I apply security updates, but I also want to keep my application up. So computers are really good at automating stuff. And so Locksmith is a tool for automating this process. So what Locksmith does is allows the system administrator to set a threshold for how many machines can be rebooting to apply security updates at a time, and ensures that before actually taking a reboot, a machine talks to Locksmith, asks, hey, can I take a lock to reboot? And then if a lock is available, it takes the lock, reboots, and then gives the lock back to the service at the end of applying the update. And so what this allows for is for system administrators to balance the I want to keep my application up with the security concerns of actually applying updates. And it's a system that we're continuing to integrate into systems like Kubernetes, so people will have visibility into through the Kubernetes API whether a machine is in need of an update and whether it should update, etc.
So there are a variety of systems that are built on top of etcd or on top of the schedulers that use CoreOS. They're systems that help with service discovery. What are some of the different approaches that are taken for service discovery in systems that use CoreOS?
Yeah, so it runs the gamut of every possible method that's been used in the past. So on top of etcd, we have systems like confd, which will do service discovery by like rewriting configuration files for you. We have things like SkyDNS, which is a DNS server built on etcd, which will allow you to do wildcard DNS discovery. You can have a hierarchy of DNS records and this sort of thing. You have systems like Vulkan, which are actually load balancers. So you input into the Vulkan API what backend services exist, and then Vulkan will actually watch for the health of those systems and make decisions across the cluster of load balancers about what backends are healthy and unhealthy and that sort of stuff. And so there's various ways that you can piece together service discovery. And then what Kubernetes has done is it's essentially a meta API for service discovery, and it provides essentially all three of those options. So using etcd as its backend, Kubernetes provides service discovery through load balancing, through DNS, or through configuration file rewrites that they call secrets or config maps. And so you kind of have this interesting thing, which is very common in open source, which is there's sort of the build your own approach that has been taken with SkyDNS and confd and Vulkan. And then you have the sort of middleware platform approach, which is what Kubernetes has done, saying we'll have a unifying abstraction and then we'll provide an adapter to each of the layers as people find that their application works better with DNS versus load balancing versus something else. And you're kind of seeing all of those options available inside the etcd ecosystem.
And what drives people to make particular selections in how they do service discovery?
Yeah, in almost all cases, you'll see people go grab a tool like confd or SkyDNS because they already have an application that's running fairly well. They have a deployment pipeline that they maybe don't want to containerize yet, etc. And so they'll pull something off the shelf that is just the one piecemeal component that fixes their problem and put that into their infrastructure. And so you'll see those sorts of patterns of adoption when people are kind of in an existing brownfield application and they can't make big architectural changes. You're seeing Kubernetes adopted when people either can take a little bit more time to think through the architecture of their application or building a brand new greenfield application and want to start from the beginning with containers and service discovery as kind of first class consideration of their operational mode for the app.
So CoreOS is not just an open source project or a series of open source projects. It's obviously a company, which you are the CTO of, and your main product is Tectonic. What is Tectonic?
Sure. So one of the things that we saw with Kubernetes is that it's a really excellent open source project. It's getting a ton of adoption from users, and we wanted to provide kind of a full solution for enterprises wanting to adopt this kind of way of running infrastructure. So what we do with Tectonic is we provide Kubernetes and a stream of updates for the Kubernetes cluster and that whole stack of software. And then we add in a number of things that enterprises expect from their operational software. So we add things like monitoring, we add things like identity, like LDAP-backed identity, We have a dashboard so that people who are less familiar or comfortable on the command line or using REST APIs are able to visually inspect and orient themselves, say they're getting paged, something's going wrong. They can start to drill down there. And then we provide Quay, which is another one of our products, Quay Enterprise, so that enterprises have the ability to inspect container images, build container images, have audit and logging and policies around those container images, scan them for security vulnerabilities and this sort of thing. So we've essentially taken the Kubernetes platform that we spend a lot of time working on the open source side, and then added a number of really necessary and critical enabling features that companies who want to adopt this type of infrastructure require, and sell that as a product that we end up calling Tectonic. So,
go ahead.
No, please.
So there are a variety of these commercial Kubernetes deployments and services that come with it. Why do customers, or how do customers choose between Tectonic and other Kubernetes deployments with services? Sure.
So right now, Tectonic is the one Kubernetes product that is kind of focused on providing Kubernetes. So we've had a lot of products focus on providing, say, a platform as a service, et cetera. But Kubernetes focuses on just providing that middle ground between infrastructure as a service that you may get from like AWS or OpenStack, and platform as a service, which you could get kind of that Heroku style experience, really focusing on providing a really good experience for a Kubernetes, Google-like infrastructure control plane. And so you're right, there are products like Google's container engine, which is a hosted product. And really the difference with Tectonic is that we let you run it wherever you feel like you want to run it. So it's not a hosted product that like CoreOS manages. It's something that your operations team run behind the firewall, or you run on AWS, or you run on Google Cloud. And so it's a little bit different sort of delivery model than some of the other Kubernetes products.
Understood. So just to close off, we touched a little bit on the unikernel stuff earlier. So for people who are kind of unfamiliar with this space, how would the usage of CoreOS compare to unikernels? I mean, CoreOS is obviously the stripped down operating system that's great for running containers. Unikernels are these highly specialized library operating systems that we take away all the excess and we use them to just basically specify operating systems that are specific to our applications. How do these two models compare, and why? You mentioned you were confused by unikernels. What is confusing about them to you?
Yeah, for sure. So first is people run successfully unikernels on top of CoreOS Linux all the time. So unikernels are essentially a way of delivering software for particular language platforms, like say a Java language platform or something like that, Erlang language platform, etc. But these unikernels still fundamentally rely on a real operating system to provide that hardware abstraction layer. And so, yes, there are efficiencies that can be gained through using a unikernel, but they introduce a lot of operational complexity through not being able to leverage existing debugging APIs that the Linux kernel provides, not being able to leverage the introspection that is provided through, say, the process tables that doing PSs, doing strace, a lot of the basic fundamentals that the abstraction of a process on Linux provides you. And so I think the reason that I'm confused, and I think that unikernels have some time that they need to prove out the actual operational model, is that the efficiencies gained by a unikernel are oftentimes not like large changing efficiencies for an engineering team. So generally changing efficiencies for an engineering team are going to be on like orders of magnitude, like a 10x improvement or a 100x improvement. And they're generally not that level of improvement. And then you kind of throw out the operational experiences that your team have with a classic deployment method, like whether that be containers or application packaging through package management, et cetera. And operational costs are a majority of the costs for an application. And so the proof that needs to happen is, well, if I'm losing my operational experience, which is the majority of the cost of running my application, and I'm gaining less than an order of magnitude efficiency, then why am I actually deploying this technology? And I think that's where unikernels kind of have to prove themselves. Is the cost really worth what you're losing?
Okay, well, that's a great place to close off. Brandon, I want to thank you for your time. This has been a great conversation, and I appreciate you coming on Software Engineering Daily.
Yeah, for sure. Thanks for having me. And I just want to encourage anybody who is interested in checking out any of these technologies. We have a bunch of really great open source guides at CoreOS.com to help you get started with containers or help you get started with Kubernetes. And a really nice community if you want to check out CoreOS.com/community and get involved with any of our open source projects and try it out.
Or if they're looking for a job.
That too. We're always hiring at CoreOS.
All right. And make sure to use referral code SEDaily. No, I'm just kidding. Okay. Thanks. Well, thanks for coming on the show, Brandon.
For sure. Thanks a lot. Cheers.
Thanks to Symphono for sponsoring Software Engineering Daily. Symphono is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symphono.com/SEDaily. That's symphono.com/SEDaily. Thanks again, Symphono.
Wow.